So in last two classes or last two chapter, we have seen that light is treated as a particle. Obviously, there are other experiments where light is just treated as a wave. For example, diffraction, for example, interference, where you can just use light as a electromagnetic wave. But photoelectric effect and Compton effect cannot be explained by the classical theory. So why we are just using the concept of photon, and this concept will explain what is our photoelectric effect and what is Compton effect. So we can see the duality in a light. So light can be particle, light can be wave. It will depends on which kind of experiment you want to explain. Okay. So similarly, there are duality in a particle also. And obviously, when we will go up to the microscopic level, means at the atomic level or subatomic level, then this property is predominant. Otherwise, when you are into the classical region or in the macroscopic region, suppose you are talking about marble ball or tennis ball kind of thing, then obviously these are not so predominant. Okay. So why here duality will also come into picture. We can have enough evidence that electron can be treated as a particle. We can assume that electron is a point particle and you can do a lot of experiments. Okay. But here there are some experiment which will prove that electron have some behavior of wave. And this behavior of wave is first given by a de Broglie, and he gave the famous definition of de Broglie wavelength. So first I will explain you what is de Broglie wavelength, and after then we will try to do two experiment, one experiment for the light and one experiment for the electron, and we will try to compare the result, and we will try to understand what is basically de Broglie wavelength and what is basically the wave nature of a electron or wave nature of a particle. So what is de Broglie wavelength? De Broglie gives a hypothesis. So this is a hypothesis. There is not any proof, but obviously we can verify this thing with an experiment. Okay. So de Broglie have told if any particle, any moving particle. So this is very important. We are not talking about the stationary particle. When particle is moving, then there is a wavelength associated to the particle, and this wavelength is equal to h by momentum of a particle. So this lambda will be inversely proportional to what? Momentum of a particle, where p is nothing but identified as momentum of a particle. Momentum of particle. So this is all about de Broglie wavelength. The simple story, simple stuff, and you can just easily calculate the wavelength of a particle if you know what is the momentum of a particle. And if I am talking about here momentum, that means I am talking about the classical momentum. Classical momentum means जिस मोमेंटम से पार्टिकल चल रही है, जब जहां पे जो भी पार्टिकल की मोमेंटम है m into जिस भी वेलोसिटी से पार्टिकल मूव कर रही है. So this p is basically identified as classical momentum. So this is a very weird kind of situation. How this wave is there, and what is significant of this wave, from where this type of wave can come into picture, we have to understand all about this. So to verify whether the electron or moving electron have associated wavelength, there is an experiment, and that experiment is identified as what? Davisson-Germer experiment. Okay. But before going to Davisson-Germer experiment, let us try to go for a Bragg diffraction for a crystal. किसके थ्रू हम देख रहे हैं? क्रिस्टल का ब्रैग डिफ्रैक्शन देखते हैं. So diffraction is what? A wave property or particle property. That is completely wave property. Okay. So you can easily use this diffraction, and you can find the some parameter, lattice parameter, or some other parameters of the solid crystal with the help of this diffraction, and you can easily calculate all this thing. So let me symmetrically draw this particular experimental arrangement for a light first, that is for the Bragg diffraction, and then we will go for a Davisson-Germer effect or Davisson-Germer experiment, and then we will try to match it, and we will verify whether lambda is actually inversely proportional to momentum, and this constant is nothing but what? H. This is very interesting. Let us try to go for this. So what we have, we can have a crystal of nickel. Okay. So we have crystal of nickel, something like this. So these are the, you can denote the lattice or atom here. Okay. You can denote this atom, and we can have a very nice arrangement of this atom. So I am not going into solid state. I will just explain you what is going to happen. So X-ray of some wavelength, and let us assume this wavelength lambda is 1.65 angstrom. So X-ray of this wavelength came into this particular lattice crystal, and we just calculate the first intensity. We just calculate the first intensity of this particular arrangement. So look at what is going to happen. So suppose one light is coming here. So I am just denoting it by a straight line, because then we can easily measure the angle. And this is a D is interspacing distance. So actually this experiment is done to determine what is the interspacing distance D for nickel crystal. So we will just try to get this particular thing. So what will happen? This is your light is coming, and this is scattered at this particular angle. Another light is just going to come here and scattered in this direction. And here we can have some screen here. So at this particular screen, what you will get? You will get interference pattern, not diffraction pattern. So we are interested into first maxima. We are interested into something called first maxima. Okay, but you can just, if you will learn, you will go in the optics, you will see that diffraction pattern, it's something like this. Okay. So this type of pattern is diffraction pattern. You have maxima and minima, and all the arrangement is here. Diffraction is nothing but the one type of interference, nothing else. Okay. So these two crystal point are just treating as a source of a light. Okay. And we have already calculated this angle of diffraction, and this angle of diffraction is assumed to be what? 50 degree. So this angle of a scattering, you can say, this is angle of a scattering. So this is coming here and just go like this. And obviously, how you will measure the diffraction? What is the condition of diffraction? The path difference must be equal to n into lambda, isn't it? The path difference must be equal to n into lambda. This is for the maxima, but we are talking about the first maxima. So n is equal to 1. Okay. So look at how we are going to calculate it. So I am just giving the perpendicular distance here. I am also giving the perpendicular distance here. Okay. So make it symmetric or symmetric. Okay. This angle is 50 degree, or you can just assume phi, that phi is equal to what? 50 degree. So this is known to us because we can easily measure at which angle this is going to diffract. Okay. Now this angle is assumed to be what? Theta. ये angle को क्या कहते हैं? Theta. So this angle will also what? Theta. Everyone is comfortable? Okay. Clear है ये? And now I can just draw this particular thing. So this angle is theta. So what will be this angle? This angle is also theta, isn't it? होगा ना? Because this angle is 90. So this angle is 90 minus theta. So, and this, the angle between this angle and this angle is also 90. So this angle is theta. And similarly, this angle is also theta. Are you people able to understand this angle?
Yes, sir.
Huh? I am just making it little bit larger, so don't worry. So something like this, okay? So you have this and this thing, okay? This angle is theta. So this angle is also theta. So this angle is 90 minus theta. So this and this are perpendicular to each other. So this angle is also what? Theta. And this angle is also what? Theta. And this angle is phi. Now, are you people going to understand all this thing? Ho raha hai na? And now you
Yes,
can
sir.
just assume something like this. Okay. So this is your path difference, something like this. Okay. Now, so this distance is exactly same. This distance is exactly same. Whatever be the path difference is this distance plus this distance. Everybody is comfortable? Yes. So what is this distance? If this distance is d, then what is this distance? That is nothing but what? D sine theta. And what is this distance? This distance is also d sine theta. So if the wave is coming, and if I am talking about first maxima, that means my wave must be something like this. If this condition hold, then we have first maxima. Are you people able to understand this thing? The total path difference है वो अगर 1 lambda के equal हो जाए, then you will get what? First maxima? Yes?
Yes, sir.
So we can have 2d sine theta is equal to 1 into lambda. Now, please mind it, it is very difficult to calculate this angle. Okay, it is very difficult to calculate this angle. Hence, we can easily calculate this angle phi, that is angle of scattering. This is your angle of diffraction. Okay, this is theta is angle of diffraction. This is phi is angle of scattering. So I can easily write the angle of this angle theta in term of phi. लिख सकते ना? क्या होगा? Theta plus phi plus theta is equal to pi. So you have 2 theta plus phi is equal to pi. So theta is nothing but pi by 2 minus phi by 2. Okay. So in term of phi, and phi is nothing but what? A scattering angle. Please. This is incoming and this is after collision, it will just go into this direction. So what we can do, and this is known to you, it is very easy to calculate because you can just put the detector here and you can say what will be the angle of this particular, this is incident wave and this is after that interaction with the atom, this wave is going into this direction. So I can easily calculate this angle with the geometry. But it is very difficult to calculate this angle with the geometry. But theoretically, we have to calculate this angle and we have to write our path difference in terms of this particular angle theta. So we are making a trick. So what will be happen? 2d sine, and that value is what? 90 minus phi upon 2 is equal to lambda. Okay. And if we will take this angle 50 degree, we can calculate the value of d. What is value of d? The value of d is equal to lambda upon 2 cos phi by 2. And we know what is the wavelength of incoming wave. The wavelength of incoming wave is 1.65, and we can easily calculate this particular thing. Calculate कर सकते हैं ना? Yes?
Yes, sir.
And from there, we can easily calculate, we can put the value of lambda 1.65, and put the value of phi is equal to 50 degree, and you can calculate this particular D. This particular D is 0.91 angstrom. So this thing you will also learn into solid state. So don't worry about this. आप इसको solid state में भी पढ़ोगे. So don't worry about this thing. So we have knowledge of this all experiment. So when we have knowledge of this experiment, we can have some basic information. And what is this basic information? That incoming wave is 1.65 and D can be easily calculated 0.91 angstrom, and this is also in angstrom, and phi is equal to 50 degree. So we have all this relationship, and this theory will explain the wave nature of X-ray. So here you can easily just verify the wave nature, and it is a match with the theoretical with the experimental result of nickel, and you can easily calculate. And vice versa, if you have D, you have phi, you can easily calculate lambda also. You have lambda, you have D, you can easily calculate phi also. And once you can calculate phi, you can also calculate theta. So everything you can calculate with this particular experiment. यहाँ तक कुछ पूछना है?
सर ये पाई हमने जो 50 लिया है वो चेंज हो सकता है, मतलब
हाँ चेंज हो सकता है चेंज, बट हमें जो मैक्सिमम मिला है वो 50 डिग्री पर मिला था एक्सपेरिमेंट में. ओके, एग्जाम में हो सकता है 60 डिग्री भी दे दे. ओके
ओके
हाँ, लेकिन हमने जो एक्सपेरिमेंट किया था वो phi इज इक्वल टू 50 डिग्री पर हमें मैक्सिमम मिला था. ओके
ओके
अगर ये लैम्डा है, ये डी है, तो phi की वैल्यू 50 डिग्री थी, है ना. एवरीथिंग इज डिपेंडेंट टू ईच अदर. आर यू गेटिंग माय पॉइंट?
यस सर.
Yes, very good. So now this parameter you have to remember. Now let us change and go to the different experimental setup. दूसरा एक्सपेरिमेंट कर रहे हैं, and this is a very very interesting experiment. और इसकी कैलकुलेशन को हम देखने की कोशिश कर रहे हैं. Are you people happy up to this point? किसी को कुछ पूछना तो नहीं है? चलो एक बार खुद करना, नहीं समझ में आएगा तो हम लोग फिर से इसको डिस्कस कर सकते हैं. ठीक है, बट राइट नाउ वी नो दिस पर्टिकुलर ब्रैग डिफ्रैक्शन इन अ वेरी नाइस वे. नाउ डेविसन एंड जर्मर एक्सपेरिमेंट, 2 person was there and they done one very fantastic experiment. And what is this experiment? Name as what? Davison and name तो सही से लिखना होगा, Germer effect. Germer. What he does, he try to do this experiment with the nickel, with the electron. So there is some nickel, okay, same nickel crystal. So we know what is the value of D, isn't it? If I know this is my nickel crystal, so you have some nickel crystal, okay, and I know what is the value of D. Don't worry about this. And there is electron gun, and this electron gun can be accelerate with help of potential. So it can be accelerate with help of potential. What will happen? We have sent the stream of gun, a stream of electron by accelerating this particular potential. You can give the potential, and this electron gun can throw the electron with some kinetic energy. So, and it can easily calculate the kinetic energy in term of potential what we are giving. What will happen? It will came here, and there is a detector. So there is all places we have detector. Suddenly what we have seen, at the angle, and this angle is 50 degree, we have a peak kind of situation. Exactly this kind of situation when we have appeared into this particular diffraction pattern. So I am interested into first maxima. I am interested into first maxima or first peak we are just going to observe. You can just, and there is detector, so you can just change the direction of detector in all spherical part. So you can just changing this particular direction of detector, and you can get at the angle 50 degree, we have this particular maxima of the peak. And the maxima of the peak is also get at the value of the potential. And what is this potential? This potential is very interesting. That is what? 54 volt. Sorry, approximately 55, but we will take exactly 54 volt. Now, so what will happen? This electron will basically come with what kinetic energy? ये इलेक्ट्रॉन किस काइनेटिक एनर्जी से आएगा? P square upon 2m is equal to what? Let us assume this value is V. So it is E into V. And from here, we can easily calculate the value of P, and that value is equal to 2m. And this is your kinetic energy, the value of kinetic energy. And from there, we can put the mass of electron, we can put the V as, and you can write this thing as 2m E into V. So here you can calculate the momentum. So you can just calculate it. I have calculated already this thing. So if we are just going to calculate this particular momentum, or this momentum is approximately, you can calculate, and that value is equal to 40 into, let me write this thing correctly, 10 to the power minus 25 kg meter per second. So we have calculated this particular momentum, and we have already draw some figure. What is this figure? When we will get potential versus, and where you are getting this particular peak, this is current versus wave, sorry, current versus potential. So at the potential at 55 degree, we have the maximum intensity, and the same thing we are just going to calculate at the intensity versus angle, and we are getting at the, this is at 54 degree and this is at angle 50 degree. We are getting the maximum peak. So this is my momentum we have calculated from here. So why we are getting this maximum peak? This is very interesting. Why we are getting this particular maximum peak? And this is just a diffraction pattern of this particular electron is going to interact with this nickel crystal. You will surprise when you will calculate the lambda with the help of de Broglie hypothesis, and here we can easily calculate the classical value of momentum with this formula, isn't it? What is value of V? V is nothing but 54 volt. E is your electronic charge, mass is that mass of electron, and you can calculate, and this is the value. You will get H upon P. Now you can easily calculate what is value of H? 6.6 into 10 to the power minus 34 by, what is this particular thing? 40 into 10 to the power minus 25 in term of meter. You can get this answer, and you will surprise that this value is exactly matched with 1.65 angstrom. Just you can check it, but finally once you will calculate this value, this will match with 1.65 angstrom. What is this? What is going to happen here? So look at, you have maxima peak at the 50 degree in a Bragg diffraction. What is the value of lambda? 1.65. In the last experiment, you remember last experiment? This is the result of last experiment from the Bragg diffraction. From the Bragg diffraction. This is your Bragg diffraction result. And now you can see the exact wavelength is also associated with the electron. So this peak can be explained by the theory that will tell that the wave associated to this electron of the lambda 1.65 will going to interact with this particular nickel crystal. This is your nickel crystal, and it will just give you maxima at the scattering angle 50 degree, which is exactly matching with the angle at the phi is equal to 50 degree. This is a scattering angle 50 degree. So what is this verification? किस चीज को वेरीफाई कर रहा है ये?
So light is a wave also.
नहीं, लाइट इज अ वेव तो है ही. ये एक्सपेरिमेंट किस चीज को वेरीफाई कर रहा है? दिस इज इलेक्ट्रॉन. आपको सेम रिजल्ट किस चीज से मिल रही है?
ब्रैग डिफ्रैक्शन.
एक्चुअली यू आर नॉट अंडरस्टैंडिंग क्या हो रहा है. ये रिजल्ट आपको पता है ना, ये किसके थ्रू मिला है? ब्रैग के थ्रू. और उसमें किसके थ्रू आपने डिफ्रैक्शन करवाया था? यू हैव डन डिफ्रैक्शन विथ हेल्प ऑफ एक्सरे, बाय अज्यूमिंग दैट एक्सरे इज अ लाइट, सॉरी एक्सरे इज अ जस्ट अ वेव. ये एजम्पशन के बेसिस पर हमें लैम्डा की वैल्यू पता थी, डी की वैल्यू हमने निकाला, फाई की वैल्यू निकाला. अब इसी डी के लिए, for the same D, we are doing the same experiment for the electron. What we are getting? We are getting if this potential is 54 degree and the angle is 50 degree, we are again getting the maxima, the peak of the maxima. So what is meaning of that? Means if this is my potential, this electron have some kinetic energy due to this accelerated potential, and this kinetic energy have some momentum, that is p square upon 2m. Hence it has some momentum, and this momentum is exactly this thing. That means if it has momentum p, that means there is a wave associated with this momentum of what wavelength? Of exactly 1.65 wavelength. So actually the wave associated with this electron is going to interact with this particular nickel crystal and giving the diffraction pattern. Are you people?
सॉरी सर, आज लेट हो गया आने में, मुझे मैसेज अभी मिला.
अभी तुम्हें मैसेज मिला?
हाँ सर, सुबह पहले बोला था तो बोलते क्लास नहीं होगा, तो उसके बाद मुझे अभी मैसेज मिला.
ओहो, कोई बात नहीं.
ठीक.
So are you people जो पहले आ चुके हो वो समझ रहे हो इसको?
Yes, sir.
Everyone?
Sir, is it proving the Broglie wavelength?
Yes, it is proving that Broglie wavelength. Na? Unless until you don't have wavelength or wave associated to this thing, how you are getting the diffraction pattern? Are you getting my point?
Yes.
Anna, you are getting the maxima and minima at the different angle. So you are getting the first maxima at the angle of 50 degree with the electron also. And this electron have associated momentum, this much of momentum, by accelerating with this particular potential. And if we are plotting this potential, I versus potential, we are getting the same peak what we are plotting with I versus phi. So if for the phi, we are also getting the same peak. So that means at this angle phi, we have also maxima for the X-ray, which is wave, isn't it? So that means this electron have associated some wavelength, and that wavelength can be calculated by this particular number h by p, and you will surprise that this number will match to exactly the wavelength of a X-ray. So what it concludes? ये क्या conclude कर रहा है? It concludes that the electron can be treated as a wave when it will give some kind of diffraction pattern or some kind of interference pattern. That time electron can also treated as a wave, and there is associated wavelength, and that associated wavelength can be calculated by the de Broglie hypothesis, and that is equal to h upon p, and that value is 1.65 angstrom. Now, if
Sir,
you
ये
have any question, you can ask me.
सर ये डेविसन-जर्मर एक्सपेरिमेंट है ना?
Yes, बिल्कुल. This is Davisson-Germer effect. और इसके पहले हम लोगों ने ब्रैग डिफ्रैक्शन किया था. ठीक है?
ओके
सो ब्रैग डिफ्रैक्शन के थ्रू हम लोगों ने ये देखा था कि लैम्डा की वैल्यू 1.65 है, तो 50 डिग्री स्कैटरिंग एंगल पे हमें फर्स्ट मैक्सिमम मिलता है. वहां से हमने डी की वैल्यू निकाली 0.91. ओके
ओके सर.
और इसी एक्सपेरिमेंट को हम फिर से कर रहे हैं. वी आर डूइंग अगेन फॉर द इलेक्ट्रॉन, सेम निकल क्रिस्टल पर. निकल क्रिस्टल का मतलब क्या है? डी की वैल्यू क्या है? 0.91 एंगस्ट्रॉम. जब इलेक्ट्रॉन से भी हमने किया तो वहां पर भी हमने ये देखा कि 50 डिग्री एंगल पे हमें क्या मिल रहा है? मैक्सिमा मिल रहा है, फर्स्ट मैक्सिमा. और यहां भी हमें किस एंगल पर मिल रहा था? 50 डिग्री एंगल पे हमें फर्स्ट मैक्सिमा मिल रहा था. ठीक है? सो ये जो फर्स्ट मैक्सिमा मिल रहा है, दैट मीन्स अगर मैं इलेक्ट्रॉन को वेव मानूं तो उसकी कितनी मोमेंटम होनी चाहिए? सॉरी, उसकी कितनी वेवलेंथ होनी चाहिए? एग्जैक्टली 1.65 होनी चाहिए,
जो डी ब्रोगली से मिल रहा
है ना? जो कि 54 डिग्री पर इसे एक्सेलरेट करने पर, व्हेन वी आर एक्सेलरेटिंग दिस इलेक्ट्रॉन with the potential 54 volt, then what we are getting? We are getting exactly same peak. Okay, so this is I versus V, means intensity versus V here, and we are getting intensity versus phi. So both are matching. For the V it is 54 degree, and for the angle it is 50 degree. So if we can calculate the momentum with this 54 volt, we are getting this much of momentum, and with the help of this particular momentum we are getting this lambda is exactly equal to what? 1.65 angstrom, which is matching with the wavelength of X-ray. So what is meaning of that? Meaning of that, yes, the assumption of de Broglie is absolutely correct, that there is wave associated with electron. Okay, so which type of question you can have? You will have very simple question. They will just ask you, if this is your kinetic energy, what will be wavelength? So you can easily find the momentum, you can calculate the wavelength. So once you can find the wavelength, you can also find the scattering angle with the help of this particular Bragg diffraction. So angle भी आप निकाल सकते हो, everything you can easily calculate. Okay?
Okay.
Now, let's try to go for one basic problem. Okay. So suppose this is my profile of potential. Okay. This potential is V0, and this is 0. This is my region 1, and this is region 2. Suppose there is a particle of mass m which is moving with energy E is equal to 2V0. Energy E is equal to 2V0. So now you can just tell me what will be de Broglie wavelength associated, and the mass of particle is m. So what will be de Broglie wavelength associated into region 1, and what will be de Broglie wavelength associated into region 2? So you have, and this is your energy, and this energy is constant. Okay. So in a first region, what will be energy? Is that any? The total energy is what? Kinetic energy plus potential energy.
Potential energy.
So what is potential energy in first region? This is 0.
0.
What is potential energy? 0. So kinetic energy is equal to plus 0 is your total energy. What is total energy? 2V0. This is your total energy.
Yes, sir.
And this is your kinetic energy. And this kinetic energy can be written as what?
P square by 2m.
P square by 2m.
2m.
So what is your P here? Your P here is 4m V0. This is your, or you can write P1 for a region 1. Okay. And what is your de Broglie wavelength into region 1? lambda 1 is equal to h upon
root over of
P1.
4 P naught M.
So this will be h upon root under 4 m V naught is your region 1 de Broglie wavelength. Now let us go for region 2. What is your E? What is your E? E is equal to kinetic energy plus potential energy. What is your total energy? Is 2V naught.
Yes, sir.
Your kinetic energy is T. What is your potential energy?
V naught.
V naught.
We know.
So what is your kinetic energy now?
V naught.
V naught. So now again you can write P2 square upon 2m is equal to V naught. So what is your P2? P2 is
root over
equal
of 2 M
to
V naught.
2m V naught.
V naught.
So this is your momentum in a second region. So what will be lambda 2? Lambda 2 is
Hy
equal to h upon P2.
root over of
P2
2 M
है
V
ना?
naught.
So क्या हो
Yes,
जाएगा?
sir.
Lambda 2 is equal to h upon 2m V naught.
V naught.
Okay. So this is your de Broglie wavelength in region 2 and this is the de Broglie wavelength in region 1.
1.
Okay. And now let us go for second region. Let us go for second region. Region second question. This is your question number 1. Now just go for E is equal to V naught by 2. E की value क्या है? V naught by 2. So what will be de Broglie wavelength into region 1 and what will be de Broglie wavelength into region 2? बताइए. So region 1 के लिए क्या होगा? Again we will go for E is equal to kinetic energy plus potential energy. And again what is your potential energy?
0.
0.
0.
And your total energy is V naught by
2.
2. So this is your P square by 2m and P is equal to, you can go for m V naught. है ना?
Yes, sir.
And what is your lambda 1 into second case? What is lambda 1? H
H
upon
upon
root under m
M V naught.
V naught. Okay. So this is the de Broglie wavelength into region 1. Now what about region 2? If you will go into region 2, then you have to be very much conscious. What is E? E is nothing but kinetic energy plus potential energy. And what is
Sir,
your
ये होगा नहीं,
potential
sir.
energy? V naught.
V naught.
And what is your total energy?
V naught by 2.
V
Not
naught by
possible,
2, and which is equal to kinetic energy plus potential energy. And you can see that kinetic energy in this region is negative, isn't it?
sir. Yes, sir.
So kinetic energy is something called V naught by 2. Is that possible?
No, sir.
No, it is not possible. So this region is what? Classical allowed region or classical forbidden region?
Classically forbidden region.
Classical forbidden region, because you cannot have particle into this region. You can have only particle if your total energy is greater than your potential energy. So is that concept of de Broglie can be applied into this region? If we will apply the concept of de Broglie into this region, we will have imaginary wavelength, isn't it? Imaginary
Yes, sir.
momentum. And there is not any scope of imaginary momentum in a physics, isn't it? Momentum
Yes, sir.
should be always a
Positive.
real number.
Real number.
That should be real number. So when we are talking about H upon P, this is very important, H upon P, then particle will always remain in classical allowed region or forbidden region or both, or in both region.
The classically allowed.
Allowed
That should be
region.
always in classical allowed region. So this momentum is actually your classical momentum. Are you getting my point? Classical momentum. And in this region, there is not any de Broglie wavelength is associated to the particle, because particle classically cannot come into this region. Classically, इस region में आएगा ही नहीं. So we cannot have any de Broglie wavelength. The concept of de Broglie wavelength is only when you have magnitude of momentum should be some real value. Okay. So
Yes,
in
sir.
this case, this is not allowed. So not any de Broglie wavelength is associated. So the concept of de Broglie wavelength will open the door of quantum mechanics. But
Yes.
actually this momentum is classical
classical.
momentum. ये जो momentum है वो कौन सा momentum है? This momentum is
Class-
nothing but what? Classical
Classical.
momentum. Okay. So we
Yes, sir.
will also try to understand how this de Broglie wavelength will come into picture with the help of group velocity and phase velocity
velocity.
into next class, and we will also do some more problem based on de Broglie hypothesis. यहाँ तक clear है ना?
Yes, sir.
Everyone is comfortable?
Yes, sir.
If you want to ask anything, you can ask right now up to this. So we have just go for the two experiment. One is Bragg and Davisson-Germer, and then we have make a hypothesis. That hypothesis is what? Lambda is nothing but h upon p, and that p is what? Classical momentum. Always remember that p is nothing but what? Classical momentum. Everyone is comfortable?
Yes, sir.
Okay. So you can just go and revise with your material. है ना? Everything is given into material, and we will do some problem into next class. कल की class में करेंगे. First we will go for group velocity and phase velocity, and then we will do the problem based on de Broglie hypothesis. Okay.
Okay, sir.
And one more thing, it is also very important. You have to always keep in mind. This is very interesting. When your V or energy, if your energy is in term of electron volt or volt, you will use the classical result of momentum. Okay. But sometime your energy can be kilo electron volt or mega electron volt. Then what you will do? You will go for what? Relativistic momentum. Okay. So you have to be very much careful when you are using the relativistic momentum and when you are using the classical momentum. समझ में आ रहा है आपको?
सर ये पॉइंट थोड़ा क्लियर कर दीजिए थोड़ा.
मैं बता रहा हूं, अगर कम एनर्जी से कोई एक्सेलरेट हो रही है पार्टिकल, फॉर एग्जांपल इलेक्ट्रॉन वोल्ट और वोल्ट, है ना, सब वोल्ट तक है, तो फिर आप वहां पर किसका यूज करोगे? यू विल जस्ट गो एंड यूज द क्लासिकल मोमेंटम, और काइनेटिक एनर्जी इज इक्वल टू p स्क्वायर बाई 2m. Okay, but sometime your energy will be in a range of mega electron volt or kilo electron volt. Okay, then you will use what? Relativistic momentum. Okay.
सर ऐसा क्यों है सर?
Because if you are accelerating something with the speed of kilo electron volt or energy with the kilo electron volt or mega electron volt, the speed will be order of 10 to the power 8 or 10 to the power 7. Okay.
Okay, sir.
So if speed is approximately go to the speed of light, then obviously you have to use what? Relativistic momentum. ठीक है?
Yes, sir.
Okay.
Sir,
हाँ.
is this de Broglie wavelength true for every particle?
Yes, this is true for every particle. Every moving particle in classical region. Obviously, if particle will move, that region is classical region. And this is true for every particle. It is very nice question. It is true for every particle, but is that it is significant to you or not? This is most important thing. Are you getting my point? Sometime your de Broglie wavelength is not significant because it has very small number. Okay. Are you getting my point?
Yes,
Hello?
So for microscopic particle, it is valid.
That is all depends on what is your choice of theory or experiment. Okay. That is nothing called microscopic and macroscopic. This de Broglie wavelength can be calculated for your tennis ball also. It can be calculated for your marble ball also. It can be calculated for your atom also. It can be calculated for your proton also. It can be calculated for your electron also. But thing is that whatever the calculation you have done for the marble ball or tennis ball is significant for you or not. Are you getting my point?
Yes, sir.
जो नंबर आपको मिलेगा वो आपके लिए सिग्निफिकेंट है या नहीं, इसके ऊपर डिपेंड करेगा कि आप उसको डी ब्रोगी हाइपोथेसिस को मानते हो या नहीं मानते हो. बट डी ब्रोगी हाइपोथेसिस इज ट्रू फॉर every particle, either it is microscopic or macroscopic. ठीक है?
Yes, sir.
Sir, if it's too less, we don't have to consider it. Is that what
Yeah,
you said?
yes, exactly. If it is too less, then obviously you can neglect it. Okay?
Okay, sir.
That is the main thing. That is the main thing. But theory is applicable on both microscopic and microscopic. You
Okay,
cannot say that your tennis ball doesn't associate de Broglie hypothesis, de Broglie wavelength. You cannot say if I am moving, then I am not associated de Broglie wavelength. I have also associated de Broglie wavelength, but that is not significant for you. Okay?
Okay, sir.
Okay.
Okay.
So this kind of question can come into your exam. Okay? That in the theoretical part. So you have to be very much crystal clear. De Broglie hypothesis or the lambda is equal to h upon p is for all particle into which region? Classical allowed region. That means your total energy is greater than potential energy. Okay?
Yes.
चलो आज के लिए इतना ही रहने देते हैं, कल हम लोग और इसके आगे बात करेंगे. और प्लीज प्रिपेयर फॉर टेस्ट ऑल्सो, है ना? टेस्ट के लिए प्रिपेयर करते रहो.
Yes, sir.
Okay, you have
Okay, sir.
2 tests. One test will be Compton and photoelectric effect, and one test will be de Broglie, uncertainty, and Bohr-Sommerfeld theory. Okay?
Okay, sir.
Okay. Chalo, thank you.
Bye. Thank you, sir.
Thank you, sir.